So as I said, the notes are there on in the news, and you can follow along the notes with the lecture, or you can look at them later. But these notes do relate to the lecture the PowerPoint pages. Wrong PowerPoint. That was the one we just finished. And where is the PowerPoint that I want? This one. So Yella, let's go. So I'm not going to go back to the notes. You can look at the notes yourself in your own time. I do recommend that you do that, though. All right. So let's talk about programming languages. So supposing we had a recipe, we talked about that kind of at the end of last lesson. That's just telling me that we got a video from the previous lecture that's available. I'll have a look at that later. So we have a bunch of ingredients and we have some instructions. This could be like an algorithm, right? So an algorithm would be used for you to solve a problem, especially to solve a problem with a computer if you're doing a computational algorithm. Algorithms don't have to work with computers, but they could. And so here's an algorithm. A recipe is an algorithm that works without a computer. This is just people do this algorithm. But what's important about the algorithm is that it has steps. It's step by step. The order is important, right? We're not going to take all the things and put them in the oven before we mix them up, right? We have to do things in the right order or the cake doesn't work. And it's same with our computing programs. The order is important. So it's step by step in the right order, right? The right thing at the right time. Also, we need to have the right ingredients. You can think of the right ingredient, the ingredients as the data. And the data has to be in the right order. The steps go with the data, right? So some data now, some data later. We don't put all the ingredients to start with, right? Now, I'm not great on this, but I have made a cake a couple of times, and I start with the butter and the sugar and the flour. There's other things I don't put in until that's mixed in properly, because otherwise it doesn't mix very well for me. I'm not great. I can make pancakes pretty good though. All right, so here's this represents the fact that we can represent that algorithm in many ways. So here's an algorithm which actually represents a how would I say, a story that was misunderstood. So basically we have the stick person there who thought that when they saw the sword stuck into the rock, they thought that that was Excalibur. Excalibur was the magic sword that was going to make King Arthur into King Arthur. And so he thought, well, there's Excalibur. I'm going to pull that out of the rock and then I'm going to be killing King Arthur. I must be King Arthur because there's Excalibur. But misunderstood, or else either he misunderstood the rock, or else he thought that he was Arthur and he wasn't, because it turned out to be not so good for him, right? So there's a thing there. Now that could be represented in another way. This is the same story, but it's represented in words instead of in a diagram. So we're representing the same story in two different ways. Here we got it in words. The guy came along, saw the stick. Everything was represented in the diagram. And that's the same with algorithms for computer programs. We can represent them in more than one way. Now there's two ways. There's three or four, I don't know, but we're going to start with these two ways. Flowcharts, and it says algorithms and flowcharts. We should say pseudocode. Pseudocode we can use, and flowcharts we can use. Now, here is a little interesting note about that. We have a problem-solving phase, and we have the implementation phase. The problem-solving phase is where we come up with a, I guess you could say, a step-by-step in our mind, and then we put that on paper or something. But basically, we come up with the steps that are required to solve the problem. The implementation phase is we're going to put that into a computer program, and we're gonna make it work, and we're gonna test it. So implementation phase requires a computer language. The problem-solving phase can be done just using algorithms with, for example, using flowchart and or pseudocode. All right, so what is an algorithm? Algorithm is step-by-step instructions to solve a problem. All right, and so algorithms can be represented as plain English, where we would just write down in a bunch of words, like a paragraph, how we think we're going, or a bunch of paragraphs, how we think we're going to solve the problem. Pseudocode is kind of enhanced English, I guess you could say. And in fact, some people used to call it structured English. So structured English is kind of like a synonym for pseudocode. So pseudocode looks like English, but it's structured. So we have some special parts to it that must be present. We must have a beginning, we must have an end, and we tend to indent things that are, we have a hierarchy, I guess you could say. So some things are related to other things in our pseudocode. A flowchart could represent the same problem, but using symbols that are graphical symbols, the shape meaning something. So with a flowchart, we have shapes that actually each different shape means something different. And the people who are looking at the flowchart and the people who created the flowchart know what those meanings are. So here's an example of both of those two things. We have on the left the flowchart, and we have 1, 2, 3, 4 different, no, 3, 1, 2, 3 different shapes here, right? Because this shape is the same as that shape, and this shape is the same as that shape. So our shape with the rounded edges, that's a connector shape, and that's used for start and end here. If we had more than one page that we were doing this flowchart on, we would have something here which would say, you know, go to next page or go to page 2, all right? And then on the other one, we'd say from page 1. And so we could use this as a connector, or we can use it as a start and end. Now this one here, which is a parallelogram, I think you'd call that, but it's not a rectangle because it doesn't have right angles. So that represents inputs and outputs. In this case, it's only inputs. Then this one that is a rectangle, the one that actually is a rectangle down there with the pay is equal to hours and rate. That is a process. So if we have a process, the computer is actually computing something, then we show that as a rectangle. So we got here data input coming in these special parallelograms, and we got here a process. Now in the pseudocode, we haven't really separated those out, have we? We just got, so we got some inputs here, and we just said input, and we got print, which is an output. That's actually missing from the flowchart, but that's okay. Okay, let's go to the next one. Let's do an example of this one. Write an algorithm to determine a student's final grade and indicate whether it's passing, failing. Now, I'm not going to make you sort of do that too much. I don't think we got enough time to sort of do it. So I'm going to whiz through it, and you'll be able to sort of see that way. Now, we could do this like this. In pseudocode, we could say, okay, you got 4 marks, let's input them. Then we're going to calculate the average by adding up the marks and dividing by 4. You agree with that? So you would do that, right? If the average is below 50, print fail. Otherwise, print pass. So final grade, whether they're passing or failing, they have to do the average of 4 marks. So that would be that. Yes? Are we going to have an if? Yes, you'll see the if. So yes, so we have this input, those marks. If we have enough time, I'll do this for you in Python. So we can see it if we have enough time. All right. So we got to finish by what, 6? Oh, what? 4:30, 5:30, 5 o'clock? Yeah, I don't know if we'll have enough time. We'll try. If we have enough time, I'll come back and I'll do this for you in Python, so you can see the if and the else, and that all works. So here we've got some inputs. Now in Python, you'd have to do each of those separately. You know, input this one, input that one, input that one. You could probably do it in a loop, you know, while not. Yeah, we could do that. Then you calculate this as an average. And then if the grade is less than 50. Now, where is my flowchart? Maybe it comes up later. Anyways, so what do we got? Algorithm is a sequence of steps. You solve the steps. We have inputs, we have outputs, and we have operations. She calls them operations. I called them processes, right? So they were the things here that was the square. In our pseudocode, in this case, calculate the average is an operation, right? Also, this test here, I guess you could say, the if statement could be, I guess, an operation. Whenever you're comparing things, we're doing what we call sort of Boolean algebra. This is bigger than or less than Boolean algebra. So that is a operation. So we got operations happening here with the calculating grade. We got an operation happening there with the if statement. Printing, that's output. Input is that bit. All right, so I think we've said enough about that. Now, what is this? This is the program that we just talked about there, represented again in two different ways. It's the same program, right? Here we got the pseudo code. Now notice the pseudo code has indents on it. We got a begin and an end. And then the if statement, what this indent here means is this fail will only happen if this thing is true. The then means it must be true. So if it's true, we're going to do this. Else means if this is false. If this is false, we do this. So the if then else, the way that works is if it's true, we do this thing, the then. If it's false, we do that thing, the else. And we only do the false if it's not true. And if it's not true, we don't do the then. If it is true, we do the then, but we don't do the else. Does that make sense? Now, how that's represented in a flowchart is like this. We have a diamond. A diamond is used for a decision box, a decision we see. So what's happening here is we calculated the grade from those. If the grade was less than, if it's true, we do this. Yes means true, right? So if it's true, we do this. We only do this if it's true. If it's true, we don't do that stuff, right? But if it's not true, then it's false. N means false. And then we do this stuff, but we don't do that stuff. Does that make sense? It doesn't. Oh my God. Didn't get it. All right. So what I'm trying to represent at the moment is that we have a choice that we can make. If, then, else. It's either true or it's false. Yeah, they are. I'll show you at the end because I just took it off D2L. It's the one that says Suzanne. Okay, so there's two lots of slides for, this is lecture 4, there's lecture 4, and then there's lecture 4 Suzanne. This is the one that says Suzanne. So there's two different versions of slides. Somebody will like, oh God. I don't really, probably a student. Yeah, it is. Okay. So what if we were going to convert feet to centimeters? Actually, it's not exactly 30. I think it's 30.84 or 30.48 or something like that. It's almost 30, right? Because it's not, anyways, but near enough. So we'll say that there's 30 centimeters in a foot. It's not exactly right, but it's kind of close to. So what would we do if we wanted to have a program that would convert feet to centimeters? We'd probably input the number of feet. So we got to, then we'd calculate the number of centimeters. Did you find it? What's up? It's the one with Suzanne. And then we'd print it after we calculate it. And so that's represented there. Do you remember this symbol? Oh, look, we got a special symbol for printing. That's nice. And there's our process, or what did she call it? I call it processing. She called it operation. Yeah, all right. So, and then there's, and look, she's done very nice start and ends. They're a little bit more rounded, so that's more obvious that they're not square. So those are our connectors. And that's a very simple algorithm and simple pseudocode. So this is very nice because it explains all those symbols that we use in a flowchart. Now, if you want to draw flowcharts, you can go to, I would recommend that you go to draw.io, which will send you to another, that'll send you to another website. But draw.io, you'll find there that you can do lots of different types of diagrams. And one of the diagrams you can do there is just choose flowcharts, and it'll give you all the symbols. You just click on the symbol and drag it on the page, and then there's arrows. And so you don't need to be sitting there, with paint trying to do this, right? There are actually programs that make it a lot easier for you to do this. So yeah, I recommend draw.io. It's free. And and it's online. So you don't even need to download an app. It's online. Now there are others where you can download apps, but yeah. Okay. So we've got a terminal symbol, and I called it a connector. Terminal is nice though. Start and end, or you could do a connector process. That is what I called it. We've got our input output symbol, our decision symbol or selection symbol, and here's a printer output. Yeah. Okay. That is correct. That looks like a piece of paper, doesn't it? And our flow lines. Now, I think in the first flow chart that we showed, we didn't have flow lines. They should have flow lines in them. The arrow showing from the start to the end how the program proceeds. And maybe that's in here. Yeah, see those arrows? So meaning that we start here, then the next thing we do is there. And if we have something a little bit more complicated, you can see that when we get to here, we either go here, the arrow goes there, but eventually we get to the stop. And notice that these arrows don't go back on each other. So you're only going one way or the other. Now, somebody didn't understand this decision thing. So I'm just going to repeat that. The decision thing. What happens here is we do a test. The diamond means test. Test, choose. What's going to happen is we've computed the grade here. So grade is a variable and it has a value, and the value is going to be tested here. And it's going to be tested here. And depending on what that value is, if that value is less than 50, then the result of this decision is true. True means that this condition is true. So where's the cursor? I mean, it keeps disappearing on me. So if this is true, then we do this. So that's why we say if then. If condition, then we do this. Else, then else means it's not true. So that would be the N. Then we do this. We don't do both. We do one or the other. That's what it means when we see these diamonds, is only one of these things can happen. So which one will it be? It depends on if the condition is true or false. Does that make more sense? Yeah, all right, good. So that's how that works. Conditions very important in programs because we call that branching. It allows us to have a different path for the program to flow depending on what's happening with it. Yes. Can't both be true. Oh, yes, the pseudo code works the same as a flow chart, correct. And so the same thing is happening here. Here we do the test. We either do that, we do this if it's true. If it's not true, we do this. There's no difference. They're the same. Yeah, these both, it's just, I guess the pseudo code is closer to programs, right? Pseudo means almost like, similar to, almost the same as. Almost the same as what? Pseudo is almost the same as code. Code being a program. So it's almost the same as a code. So when we write our computer program, it's going to look like that too. And so if I wanted to make a computer program, yeah, I could do it from the flowchart, but it would be more obvious to do it from the pseudo code. The pseudo code is going to look like my program. Okay, there's that. We went through those symbols. Yeah, okay, so it is important to note that we do have this idea of sequence. That is the first, if you come across a bunch of instructions that are one after the other, that's the way that they're going to be processed. Whatever is represented, see the arrows there, this statement is going to happen before this statement is going to happen before this statement. That's what we mean by sequence. Then when we come upon a condition, depending on if it's true, we do that. And if it's not true, we do that. Right, so that's how that works. So that's a condition. We can have a loop. And so how a loop is going to work is the loop will continue until the condition becomes false. So the way the loop works is we say a condition. If this thing is true, then just keep on doing this, right? So for example, we'll say while x is less than 10. And every time we go through the loop, we add 1 to x. Then eventually x is going to become 10, and we won't do it any more times. That makes sense. So that would be a counted loop. And what do we got there? We read their birth date, and we calculate how old they are by today's date, and then we display the age. Yeah, that's a simple program. Then we could add to that if the person is over 55. I'm not sure. I'm sorry, I didn't make these slides, made by somebody else in a language I don't understand. I think it might be Turkish. I don't know. What do you think? And I think this might be a pension, old age pension. And I don't know what that means. Kurjalagi, something. Anyway, so yeah, that's kind of nice. And okay, so what we see there is we see some inputs. Now, if the person's age is over 50, what if the person's age is 55? Which way? That's a tricky one. We don't like and we don't allow ambiguity. So if they're exactly 55, then they're not more than 55. And so that would be a no, right? And so maybe we would want to change this. You know, if the person is eligible for a pension on their 55th birthday, I would change this to greater than and equal to. But if they have to wait until they're 56, then I would just leave it as it is, because this person would get a pension when they're 56. They don't get it when they're 55, because 55 is not bigger than 55, right? So that would be no. If you're 55 and you test yourself, are you more than 55? No, I'm 55. You get the idea? So there's quite a big difference between greater than and greater than or equal to. Sorry? There's a line underneath it. Yeah, you could put, yeah. Big, I guess, yeah, sorry. I'm sorry, I'm not hearing very well. They'll be underneath? What I understand is if it's bigger than 55, 55 is not bigger than 50. Oh, yeah. Okay, yeah. That would be if you're doing mathematics. For computing, we do it like that. Yeah. So, yeah. Computing is a little bit different than mathematics. And so you can see it here, right? Greater than or less than or equal to. We do the symbol and then we do an equal to after we use them together. What's this one? All right, so we are going to count the number. So here we add 1 to the number, current number, and we have a total. So you're going to input a number, are you? Where's this? Yeah, so well, there should be another input in there, but that's all right. So it's missing one step, which would be some kind of input. But yeah, but the cool thing here is we add, no, that's all right. We add 1 to the number. And so that is our input. That's fine. We start off with a number of 1, and we're going to go through here. And we're going to add 1 to 1 every time until we get to 10. And then we're going to print the sum. That's kind of cool. I should have looked at that before. Oh. Basically, this slide just says that we have to take the algorithm and we have to translate it into a computer program. And then that computer program will be used by another translation to get our zeros and ones, a machine code. That's all that's saying. With low-level languages, the language is very similar to machine code, so the translation is not that great. With higher level languages, and here we have that, and so I'm running out of time, so I kind of do this fast. This is what the computer understands. The computer understands 0 and 1. This is machine code. Oh man, I should do this over here so people watching can see. This is machine code. And this is the same as that. The thing on the right is the same as the thing on the left. The only thing that we've done is we've converted these binary numbers to hex numbers. And I'll show you how to do that tomorrow in class. We'll have a special lesson where we just look at binary numbers, hex numbers, and decimal numbers. But this is basically the same as that. So this, again, is just machine code. Zeros and ones, or some representation of zeros and ones where we've converted them to hexes. But basically, this is just zeros and ones. That's what the computer understands. Now, that problem with that, it's easy for the computer to understand. It's not as easy for people to understand it. And so we came up with same programming languages, assembly language, which is the second generation language or second layer language. This is first layer or first generation language, which is zeros and ones, machine code. Second generation or second layer languages is going to be our assembly languages. And they have some special codes that we can use. So you can, and here we see some explanation of what those codes are. ORG for origin, load, operand, add, Okay, so we have some special commands that we can use. We still have to specify the location in the memory where we're going to get the data and use the data that we're working with. So this is second generation. Still a lot of dealing directly with the memory, so it's a lot of steps and it's kind of hard to do, but at least a human can sort of interact with it without just memorizing a bunch of zeros and ones codes. A third generation language or higher generation language, you see here with the C programming language. Basically, all of these programs are doing the same thing from what I can gather. And so in C programming language, it's a lot more, how you say, related to the human. So the human programmer can look at that and sort of say what it's doing. So the human programmer is going to look at that and say, well, you know, what I'm going to do is I'm going to have 3 variables. Variable is a space in the memory, just like these locations in the memory here, but I don't have to say where they are. The computer is going to do that for me. All right. The operating system and the programming language are going to work together and get the place in memory to do that. I don't have to know where it is. All I have to do is to tell it to do it. So that's good. So the computer's starting to do stuff for me instead of me having to do everything. Now, but I do have to, where are you there? But I do have to tell the computer what type of data this is. So I have to tell the computer that these are all integers. And so I do that by saying int. And then I got 3 variables. So I'm going to have 3 spaces in the memory. 2 of them I actually have a value that I assign to them. So A is going to be a variable in the memory, and it's going to have the value 83, which is an integer assigned to it. B is going to be a place in the memory that's going to have the integer, I think it's minus 23 assigned to it. And C doesn't have anything assigned to it yet. Then I'm going to go ahead and I'm going to put a value into C, but it's going to be the sum of these 2 numbers. The same program over here in, let's move that out of the way. The same program over here in Python, which is a very high level language, very high level language. I guess we could say that as we go up in levels of languages, what we're getting is more help from the computer for us. So it's more natural for us as programmers to work with it. And so we don't have to tell the program this time what kind of variable I've got. All I have to do is say, I got a variable A, I got a variable B, and just put a number in it. Python figures out that it's an integer. We don't have to tell it. So we say here that C programming language explicitly types. We use the word type because there's types of data. You have integer data, you have float data, you have character data, you have string data, you have Boolean data. Okay, so we got different types of data. With Python, we don't have to tell it what type of data. Just give it the data and Python figures it out. So it can see that the number 83, well, that's an integer. It'll store it as an integer. Number minus 23, that's an integer. Now, if it was a float, it would just store it as a float. That's fine. Now, what is a float? Float is a number that has a decimal part to it. All right, you know, and integer doesn't have any decimal parts to it. So then C just takes in the value of that. So Python, I think you'd say, is more natural. It almost looks like a little bit of math, right? Just look there, just say these things. And so it's natural for us. It's easier for us to program. Does that mean that Python is not a powerful language? Actually, you might say that Python in some ways is more powerful than C. Now, C is powerful. I mean, so I got to be careful what I say about C. People write operating systems using the C language. All right, so it's a very powerful language. Engineers use C a lot. But Python is also used by engineers. What makes it possible is Python has a lot of libraries attached to it. So you as a computer engineer, you can use Python to, it has tools in libraries that you can do modifications of an operating system. You can use Python to program your switches and routers in a network, okay? And you can use Python as a plugin to your web pages. Yeah, I mean, so I want you to know that it's a very powerful language, very useful. And the reason why I'm saying that is because you will be programming in Python, whether you're a network person or a software person, you're going to be doing some Python programming. And we're going to do some in this class. Last slide for today. Hooray. No, it's not. She added some more slides. These represent various programming languages that you will come across and you'll probably have to do. If you're going to go into the software program, you're going to have to program in JavaScript and PHP. JavaScript allows for what we call dynamic web pages. That is that the user can interact with the web page and the web page actually changes. Not just going to a new web page, but the web page actually changes depending on what the user is interacting with it. PHP allows you to connect your web page to a database server. So your database server would typically be a SQL server. Doesn't have to be though. But if you want to use a website for any kind of business, you're going to have to store transactions, right? We store transactions in a database. So you would be using probably, now Java is very similar to Python. Java is a little bit older than Python, a little bit harder to program. Java looks a lot like C, and it's kind of like C. Python is like Java, but maybe, as I said, does some things automatically for you. But now these other ones are in Ruby on Rails. As far as I know, they're used by people in big data and sort of artificial intelligence things. So what they're able to do is sort of take big data sets and find patterns in them. C++ is a advancement on C. It looks like C, but it's more powerful. It's kind of like Python and Java in that you can use it for it is an object-oriented language, so you can create objects and classes and methods and things like that. That doesn't mean anything to you now. Don't worry about it. I'm not going to give you a test on what are objects, but just sort of keep that in your mind because you'll be using that when you do your programming later. Okay, so let's look at this. So we've got, assembled, compiled, and interpreted languages. So we have assemblers, interpreters, and compilers. Assemblers are going to take your second layer languages and turn them into machine code. So if you had assembly, you would take assembler and work with that. That was our first way of doing programming. Then, as it says, works with assembly language. Let's just leave it at that. Interpreted languages, what we're doing. So in all of these things, assemblers, interpreters, and compilers, what we're doing is we're taking the program that was written by a human, which is something that kind of looks like English in a way, and put it into zeros and ones, machine codes. The computer can only work with machine codes. So if you had the assembly language, remember that was the one with the LDA and that the second layer language, then you'd use assembler to do that. If you're working with a higher level language, you could use an interpreter, and you could use an interpreter or a compiler. So the difference between an interpreter and a compiler, an interpreter is going to take the code, one line of code at a time. It's going to translate that and put it through to the CPU. That's good because it means that you can interact with the program as it's running. When I say that, you're interacting with the interpreter. It's kind of bad because people are going to see your code. So if you distribute a interpreted code, people are going to see the contents and they could change it. Maybe you like that. Now with a compiler, what we do is before we even get it anywhere near the CPU is we take the whole program as one big block and we just turn it into machine code. And so what you end up with when you run something through a compiler is you end up with a program which is going to have an extension of like DLL or something like that. So I mean, with a Python program, you're going to have your program is going to be a .py. You can open that with an editor, any editor. You could open it with Microsoft Word and you could read it. I see what he's doing. I'll steal that. Or I see what he's doing. I'll change that. Right now, when you write your program, you take your Python and you compile it. So with an interpreter, you're going to have that. You compile it. You're going to get a DLL or a exe or a COM file. And when you open them up with an editor, you can open any file up with an editor. You open it up with an editor, all you can see is zeros and ones. What does it mean? Well, I don't know. Actually, probably your editor is going to open it up in hex code. So you can see zeros, ones, A, B, C, D, E, right? So it's going to be like that because that's typically how we do it is our editors are going to take the code and show it to you in hex. But you won't be able to understand it. That it's sort of hiding the details from you. And the other thing is the code is compressed, so it runs really fast. And so compilers are better for a few reasons like that. So there's a bit of that about it. And so we have source code and object code, etc. And I think I'm going to finish there. Unless there's, so I'm going to stop. Maybe you have some questions. If not, you can go. It's kind of up to you. So see you later, Faisal and Sami and Huzaifa. And sir, you have posted an assignment lab. The due dates are at the end of the week. All right, so we'll get through that, right? The assignment, yeah, actually early next week, but the lab this week. We'll do the lab during the lab time. Okay? Halas and Zain.